Hi, I'm Ernest Rutherford, a physicist from New Zealand. Today we will explore my alpha scattering experiment. Let's begin.
Let's build on the topics we covered in our last lesson. In today's lesson, we will continue this exploration by focusing on Rutherford's alpha particle scattering experiment, which proved that atoms consist of a small, dense, positively charged nucleus at its center, with electrons orbiting this nucleus. Secondly, we will examine the development of the current nuclear model in light of the alpha particle scattering experiment. Finally, we will study Niels Bohr's refinement of the nuclear model, as he discovered the way in which electrons were arranged around the nucleus. In 1909, Ernest Rutherford and his colleagues conducted a groundbreaking experiment that would challenge existing atomic models, like Thomson's Plum Pudding model, and lay the foundation for the modern understanding of atomic structure. Rutherford's alpha scattering experiment aimed to understand the structure of the atom. By shooting alpha particles at a thin gold foil, he wanted to observe how these particles would interact with the atoms in the foil. Let's look at the experiment in more detail. In this experiment, they fired positively charged alpha particles at a thin sheet of gold foil to see how the alpha particles would react with the atoms in the gold foil. Based on the prevailing Plum Pudding model, they expected the alpha particles to pass through the foil with minimal deflection, that is, in a straight line. This is because Thomson's model theorized that the atom consisted of an evenly distributed positive charge that was spread out across the entire atom. From this, Rutherford expected that this positive charge wouldn't exert a strong enough force to significantly alter the trajectories of the alpha particles. Let's see what happened in reality. We can see that whilst most of the alpha particles were not deflected and did pass straight through, a small fraction were deflected at large angles, and some even bounced straight back. Let's look at another animation for this experiment, as it is important to recognize the experiment through different diagrams. To repeat, the positively charged alpha particles were fired at a thin sheet of gold foil. While most of the alpha particles were not deflected and passed straight through, a small fraction were deflected at large angles, and some traveled straight back. So what did the surprising results of this experiment mean for the structure of the atom? Based on the prevailing Plum Pudding model, they expected the alpha particles to pass through the foil with minimal deflection or repulsion because they thought the positive charge was spread out evenly throughout the atom. However, the fact that most of the alpha particles passed through without significant deflection indicated that the atom is not a solid mass, but is instead composed largely of empty space. Rutherford's first observation was that most of the alpha particles passed straight through the gold foil, meaning that the atom must be largely composed of empty space. Secondly, some of the alpha particles were deflected by a small angle. This meant that the mass of the atom must be concentrated in an extremely small volume in the center. Finally, a very small number of alpha particles came back in the direction of the detector, which meant that the center of an atom must have a strong positive charge. This experiment also revealed that electrons must not be in the center of the atom. Contrary to what the Plum Pudding model said, instead, electrons must be orbiting the nucleus. Thus, these findings discredited the Plum Pudding model. Let's see what happened next in the development of the nuclear model. The findings from Rutherford's experiment led to the development of a new atomic model, moving away from the Plum Pudding model. Rutherford's experiments found that the atom has a tiny, dense, positively charged nucleus at its core, which held most of the atom's mass. Around this nucleus, Rutherford was aware that negatively charged electrons existed and moved around. But he and other scientists at the time weren't exactly sure about the nature of their movement. In 1913, Niels Bohr, a Danish physicist, refined this model further by incorporating the concept of quantized electron orbits. Recall from our lesson on electronic structure that electrons orbit the nucleus in shells that get increasingly further from the nucleus. For example, sodium has 11 electrons. What Bohr's refinement of the model tells us is where those electrons lie. Using our electron configuration rules, we know that sodium has 2 electrons in the first shell, 8 in the second shell, and 1 in the third shell. The idea of shells is precisely what the Bohr model added. Prior to this refinement, it was not known how electrons behaved around the nucleus, or where exactly they were. Bohr suggested that electrons orbit the nucleus at specific distances called energy levels, similar to planets orbiting the Sun. Much like planets, electrons cannot go in between orbits. They can only exist at their particular energy levels. That's all for today. To summarize, we understood how Rutherford's experiment revealed that atoms are mostly empty space with a small, dense, positively charged nucleus at the center. This discovery challenged the existing Plum Pudding model and laid the groundwork for the modern understanding of atomic structure, where electrons orbit the nucleus. We looked at how Rutherford's experiment revolutionized our understanding of atomic structure, establishing the nuclear model that introduced the concept of a dense nucleus surrounded by electrons. This breakthrough marked a significant departure from the Plum Pudding model, setting the stage for further exploration into the behavior of electrons. Finally, Bohr's refinement of the nuclear model clarified the behavior and arrangement of electrons by introducing the concept of quantized energy levels, or shells, where electrons reside. This model provided a more accurate understanding of electron distribution, explaining that electrons orbit the nucleus in fixed paths similar to planets around the Sun and cannot exist between these defined energy levels. Well done for completing this lesson, and see you next time.